Okay, then our last talk of the session is Tyler Ellison talking about Floquet codes with a twist.
Thank you for the introduction. Thank you also for the opportunity to share our work here. Unfortunately, I feel like I have to begin with a bit of an apology. This talk came together quickly, and there are a few extra slides in my presentation. It shouldn't be an issue, I'll just flip through them quickly, but I wanted to be upfront and apologize for the extra slides. So I'll be telling you about our construction of twist effects in Floquet codes. This is based on work that was done in collaboration with Joe Sullivan and Arpit Dua. Here's the main takeaway. In the previous two talks, we heard about boson condensation in the context of Floquet codes. In this talk, I'll discuss fermion condensation. By condensing fermions in a honeycomb Floquet code, we have a method for creating twist defects. These are point-like irregularities of the code that can be used to store and process quantum information and also speed up lattice surgery. The hope of this work is that we provide a new tool for building dynamical quantum error correcting codes that hopefully reduce the A to C ratio. That's the error to chip ratio. Here is an outline of my talk. And here's what I'm going to tell you about. Ultimately, I'd like to tell you about our construction of twist defects in the honeycomb Floquet code. There's a natural analog in the context of surface codes, so I'll start there. I'll begin with a very brief review of surface codes and the anion theories. I'll argue that the surface code has an emergent fermion, and by condensing that fermion along one-dimensional paths, we can build twist effects. I'll then perform the same construction in the honeycomb Floquet code to build twist effects and conclude with covering some aspects of this work that didn't make the 25-minute cut and describing future avenues for work. So let's start with setting some conventions for the surface code. I'll work with the unrotated surface code. I'll take the vertex stabilizers to be product of poly X operators, and I'll take the plaquette stabilizers to be products of poly Z operators. Just to save myself time in making these slides, I'll change the notation and use red edges for poly X operators and blue edges for poly Z operators. For this crowd, I'll define anions to be violations of stabilizers that cannot be created or destroyed by local operators. The surface code exhibits 4 types of anions. There's the trivial anion. These are violations of stabilizers that can be created and destroyed by geometrically local operators. There's an E anion, corresponding to a violation of a vertex stabilizer, an M anion, which corresponds to a violation of a plaquette stabilizer. And there's a composite excitation called EM, which violates both a vertex and a plaquette stabilizer. These are created by products of poly operators supported along a string in the lattice. Remarkably, the EM anion is a fermion. It has fermionic exchange statistics. This is rather striking because the underlying algebra of the poly X and poly Z operators satisfy bosonic commutation relations. Nonetheless, here we have an anion with fermionic statistics. For that reason, we call this an emergent fermion. So what do I mean exactly by saying that this has fermionic exchange statistics? Well, it's exactly as you'd expect. A wave function with a pair of EM anions is antisymmetric under their exchange. Let me illustrate that explicitly. So here I have 2 EM anions, and I'm going to exchange their positions in such a way that the dynamical phase, the phase picked up upon moving these EM anions, cancels. So here's what I'll do. I'll move the anion on the left towards the middle with a string operator W1. I'll move it down. I'll move this one on the right to the left. Move this up. And what I've done, as you can tell, is I've swapped the EM anions. You can see that this produces a sign from the commutation relations of these string operators. If I apply these string operators in that sequence, their product is -1. So this says that if I apply that sequence to exchange two fermions, the wave function will pick up the sign of -1, and these are indeed fermions. At the top of this talk, I told you that we were going to condense fermions. And that might sound somewhat uncomfortable. And that's because the fermionic exchange statistics are an obstruction to condensing fermions in 2 dimensions. And that can be seen directly from that expression that I wrote down. This product of string operators is equal to -1. To condense an anion, we need to be able to add the string operators to the stabilizer group. But here we see that there are at least 2 string operators which fail to commute with one another. So I can't simultaneously measure these string operators and add them to the stabilizer group. While we can't condense fermions in 2 dimensions, there is no obstruction to condensing fermions in 1 dimension, or a 1-dimensional subsystem. In other words, we can simultaneously measure the string operators along a 1-dimensional path. Now, what I'd like to show next is how we can do that explicitly in the surface code. I'm so sorry about this. There are extra slides in my presentation, like I said. That was significantly funnier. All right. So everything I've said so far is a review. Now, hopefully, I'll tell you something which may be new. And that's, we're going to condense fermions along a 1-dimensional path. This will result in a construction of twist defects. This can be performed in 3 steps. In the first step, I'll define a string operator that creates EM anions. I'll decompose this string operator into short string operators. These short string operators generate all string operators along this 1-dimensional path. Then you'll notice that these short string operators are mutually commuting. In fact, their supports are non-overlapping. So there's no obstruction to simultaneously measuring these short string operators, and in doing so, we've condensed the fermions along this path. We now have new stabilizers. Those are these 2-body stabilizers. We have to throw out any stabilizer that fails to commute with those short string operators. This includes the plaquette stabilizers and the vertex stabilizers. However, you'll notice that their product, the 6-body stabilizer, commutes with the short string operators. So that's retained in the stabilizer group. This indeed produces twist effects. What I've shown is that we've modified the stabilizers along the length of this path. To the left of the defect, we have surface code. To the right, we have surface code. So I'll call this barrier a domain wall. And I claim that the endpoints of this domain wall are the point-like twist defects. How do we see that? Well, twist defects exhibit 2 notable properties. The second follows from the first. Here we see that this domain wall exchanges E and M anions. If I take an E anion and move it across the domain wall, it turns into an M anion. This is to say that there's a string operator that creates an E anion on one side, an M anion on the other, and commutes with all the stabilizers, all the modified stabilizers along the domain wall. The second property is that EM anions can be absorbed into the twist defect. Again, this just means that there's a string operator that terminates on the twist defect. It commutes with all the stabilizers in the vicinity of the twist defect and creates a single EM anion. Before moving on to the honeycomb code, let me compare and contrast with the standard approach to creating twist defects. In the standard approach, what we do is we identify a symmetry of the code which acts on the full system, such as a translation symmetry in the surface code or in the toric code. Then we create a symmetry defect for that symmetry. This might be a dislocation. In this construction, however, we just make these 2-body measurements to condense the fermions. And this latter construction will be natural to implement for the honeycomb code. So let's move on. I'll repeat that same story, now in a dynamical context. We've seen the honeycomb code, but I'm going to use a slightly different convention. I'm going to use the conventions originally introduced by Hastings and Ha. If you're curious about why that is, I'm happy to field that question. In order to specify the Floquet code, I need to tell you two pieces of information. I need to tell you what to measure and when to measure them. So here's what to measure. These are the checks of the Floquet code. The checks are specified by labeling the edges of the hexagonal lattice with X, Y, and Z according to their orientations. On the X, Y, and Z edges, measure XX, YY, and ZZ checks respectively. These are the checks of the honeycomb code. Next, I need to tell you the measurement schedule. To specify the measurement schedule, we'll label the plaquettes by 0, 1, and 2 in such a way that neighboring plaquettes have different labels. I'll define the 0 checks to be those two-body checks that connect 0 plaquettes, shown in red here. Likewise, the 1 checks and 2 checks go between 1 plaquettes and 2 plaquettes. So here we have the measurement schedule. After some period of initialization, we repeat in sequence 0 checks, 1 checks, 2 checks. At each instance in time, the system can be characterized by a stabilizer code. These are the instantaneous stabilizer groups, or ISGs. Here are the ISGs for the honeycomb Floquet code. The 0 ISG, for example, includes the 0 checks. We just measured those, so those should belong to the stabilizer group. Likewise for the 1 checks and the 2 checks. But there's more here. There's also these plaquette stabilizers. And those plaquette stabilizers are common to each of the ISGs. They are products of checks around a plaquette. Now, it seems like a trivial statement, but it's absolutely crucial for what I'll tell you. And that's that these plaquette stabilizers, because they belong to each of the instantaneous stabilizer groups, they commute with all of the checks. Okay, Hastings and Ha told us that these instantaneous stabilizer groups are locally equivalent to a surface code. This is to say that they're, by adding ancillary qubits and applying a constant depth circuit, we can map the ISGs to a surface code on a hexagonal lattice. What this tells us is that these instantaneous stabilizer groups are characterized by the same anion theory as a surface code. They exhibit E, M, and EM anions. Now, using this, we could hope to build twist effects in the honeycomb code using the standard method. We identify some symmetries of the instantaneous stabilizer groups and construct symmetry defects. However, it's not clear whether there's a symmetry that acts on the full system and is shared by each of the ISGs. However, what is shared and what will allow us to build twist effects is the fact that each of these ISGs have plaquette stabilizers. Intuitively, these plaquette stabilizers can be interpreted as small loops of emergent fermion string operator. How do we see that? Well, I can take a product of plaquette stabilizers over some large region R. All of the Pauli operators in the bulk of this region cancel, and we're left with a string operator supported on the boundary of R. Now, I already told you that the plaquette stabilizers commute with all the checks, so this long string operator will also commute with all the checks. Now we'll truncate this string operator. Let's just cut it. We know that it commutes along the length of its string with all the checks, but it may fail to commute with the checks and the stabilizers at the endpoints. And it can be verified that, in fact, what this string operator does is it creates EM anions. And this is true for all of the ISGs. This is important because what it means is that the same string operator can be used to create EM anions for each of the ISGs. That means the same short string operators can be used to condense fermions in each of the ISGs. At this point, the construction is embarrassingly simple or surprisingly elegant, depending on how much water is in your glass. What I'll do is follow the same prescription to condense fermions in the honeycomb code. I'll define a fermion string operator along a path. Here's an example. You can cook up more contrived paths if you'd like. I'll decompose this string operator into short string operators. In most cases, this can be done with two-body operators. Then I'll define a new set of checks, which are those short string operators. We want these short string operators to belong to the stabilizer group because that will ensure that the fermions have been condensed along this path. So to do that, we actually need to throw away some measurements. We'll throw away any of the checks that fail to commute with those short string operators. So I've denoted that here with these dashed lines. We no longer measure those two-body checks. These are the checks of the honeycomb code with a pair of twist defects. Next, I need to tell you the measurement schedule, and that'll specify our Floquet code. There's only a mild generalization that's necessary to build our honeycomb code with twist defects, a mild modification to the measurement schedule. Since by construction, we've thrown out any checks that fail to commute with our short string operators, we can measure them at any point in the schedule. We might as well measure them at the same time as the zero checks, or whatever's most convenient. Then our schedule is really just zero checks, along with those condensation terms, one checks, two checks, and repeat. And I've claimed that this produces twist defects. How do we see that? We can go ISG by ISG and see that there's a pair of twist defects in the instantaneous stabilizer groups. So here's the zero ISG. It, of course, includes the zero checks, except for the ones that have been removed along this domain wall. It includes the two-body short string operators. It includes the plaquette stabilizers away from the domain wall. It also includes some modified stabilizers near the domain wall. There's this horseshoe-shaped stabilizer that would appear here. And there's a product of two plaquette stabilizers that has this peanut shape, and that occurs along every removed edge. Okay, so what are the two properties of twist defects that we need to verify? Well, first, E and M anions are swapped across the domain wall. That can be seen by finding a string operator that creates E on one side, M on the other, and this string operator commutes with all the instantaneous stabilizers along its path. We can also show that EM anions can be absorbed into the twist defect, since there's a string operator that commutes with all the instantaneous stabilizers and only creates EM anions far away. Now, at this point, we can use the same methods for storing and processing quantum information as is standard in the static case. We can use 4 twist defects to encode a qubit. Here I've shown 4 twist defects. We can take the logical operators to be fermion string operators that transfer fermion parity between the twist defects. So this X logical operator, for example, is a fermion string that connects these two twist defects. The Z is a fermion string that connects these two twist defects. The anti-commutation relations comes not from the braiding of the anions, it actually comes from the statistics of the fermions in this case. Now, interestingly, these fermion strings commute with all the checks. So there are no automorphisms of the logical operators in this case, in contrast to Margarita's best codes. We can also further process information by braiding the twist defects and fusing them together. I didn't plan that. So let me just highlight some benefits of this code. Of course, the twist defects can be constructed in a planar geometry. We don't have to make any changes to the qubit connectivity. And we maintain the fact that the Floquet code is built from two-body measurements. We've thrown out some of those two-body measurements and replaced them by two-body measurements that condense the fermions. We also maintain the fact that the Floquet code operates using only 3 measurements per period. In the remaining time that I have, which I'm not exactly sure how much I have, 7 minutes, I'll slowly discuss some aspects of this work that I didn't think I would have time to discuss. The first is we have a generalization of the honeycomb code to n-dimensional qubits. At each instance in time, the ISG is characterized by a ZN toric code. These exhibit more rich or richer anion theories and allows for more exotic twist effects. For example, if you have 4-dimensional qubits, you can now condense fermions, or you can condense semions, something that has exchange statistics of a factor of I. We also showed that we can construct Floquet codes for which each instantaneous stabilizer group is characterized by the anion theory of the double semion topological order. This is constructed by taking a Z4 Floquet code and inserting semi-permeable defects via condensation in a grid-like shape. Some anions of the Z4 toric code become confined. Others can pass through these semi-permeable domain walls. The anions that can pass through these domain walls are precisely those of the double semion theory. Lastly, we also have a construction of Floquet codes in 3 dimensions, and these codes exhibit a point-like emergent fermion. Similarly, you can condense these point-like emergent fermions along a path to produce twist effects in this 3-dimensional setting. Last slide, and then we can move towards lunch. One thing that we're planning on doing is implementing these twist effects on IBM's quantum processors. It's quite natural there with the honeycomb or with the heavy hexagonal lattice because we can use the qubits on the edges to implement the 2-body measurements. Moreover, on any given day, you can go onto IBM's website and see how the qubits are behaving. Sometimes the couplings are misbehaving or broken. And what we can do is arrange the domain walls to take advantage of the broken couplings. On some of these edges, we never need to make any measurements. So we'll position the domain walls so that the removed checks lie right where the broken couplings are. This construction of twist effects in Floquet codes is also part of a larger story in understanding twist effects from a space-time perspective. In some preliminary work with folks that are in the audience, some which prefer an air of mystery about them, we have a construction of twist effects in a space-time setting where we've proliferated fermion world lines on a world sheet. This can be interpreted as the history of a domain wall, and the boundaries are world lines of the twist effects. Okay, I'll stop here. Thank you.
Thanks, Tyler, for this very clear talk. I have a question on the construction using the semi-permeable domain walls. Are you placing the domain walls on the level of the lattice spacing, or do you need to have a quite big lattice to have the effective behavior of a double semion?
That's right. This is a coarse-grained lattice. It has to be sufficiently large so that you have the Z4 toric code stabilizers in the patches. That's right. So this is on a coarse-grained lattice.
Do you know if like one pair of stabilizers survives or is sufficient, or do you really have to have like a macroscopically, not macroscopically, but like orders of 10 cells, or?
That's a good question. I'm not sure. Yeah, how large the spacing needs to be.
Thanks.
So there's a story by Ben Brown and others sort of looking at twist effects on the corners of surface codes, defining boundaries, lattice surgeries as fusions of these. Is there an analogous story for lattice surgery of boundaried Floquet codes as fusions of these defects?
Yeah, thanks. That's a good question. So Ha and Hastings, I have to switch the order for this second paper, have a construction of Floquet codes with boundaries, and they also discuss lattice surgery there. I think what you're suggesting is, similarly, we could just move these twist effects to the corners and perform lattice surgery.
Yeah, so can you move these twist effects to the corners?
Yes, that's a good question. So you certainly can move them to the corners, but something fishy happens that I don't fully understand. And that's that when you start with the Ha and Hastings construction, the logical operators are these non-contractible loops. But what can happen with when you put these twist effects in the corners is that you can have like an E anion. The logical operators can also be represented by E anions that move around a pair of twist effects. In every construction I've tried, this E anion can squeak around the edge. It can move past this twist effect. So there seems to be something subtly different, or I just don't have a comprehensive enough understanding.
I'd like to talk more about this later.
Yeah, absolutely.
Thanks.
Hey, thanks a lot for the great talk. It was very clear, and I like the slides. The thing that I was wondering, you had these really nice two ways of thinking about twist defects in even the surface code. And one of the things that I kind of remember thinking was really cool in the one that you didn't do is that you can't really see where the cut is. So the example that you use here, you can see, okay, this is the dashed line is where the cut was in your lattice. And in the other approach, locally you don't know, like the lattice looks the same everywhere, which is kind of interesting. And so I'm wondering if you know a way of doing that with the Floquet codes where you kind of locally don't see where the cut is. The lattice kind of looks the same everywhere, at least at the level of a graph.
So I would say that in both cases, you can, in some sense, see the location of the domain wall just because you modify the stabilizers along the domain wall.
Well, I remember there's a way, there is a construction where you don't. In the Hector's original paper, I think it's like that.
The one I have cited here, yeah.
Yeah, I mean, let's talk about it afterwards because it's also entirely possible that I'm misremembering this, but yeah.
Yeah, that's interesting.
Yeah.
Yeah, that's a good question.
There's a whole bunch of, I'm over here on the left. Hey, there's a whole bunch of Floquet codes. I'm confused how general this is, and you're welcome to use any of your extra slides to answer the question.
Yeah, so that's a good question. The honeycomb code is special as compared to the CSS Floquet code or these codes that Margarita and Julio talked about because it has these stabilizers that are common to each of the ISGs. In a more technical language, we would say that the checks have a anomalous one-form symmetry. It's just to say that they commute with this string operator generated by loops of fermions. That's not the case for the CSS code. The plaquette stabilizers are changing over time. So there's something special about this that allows us to condense fermions. But of course, in this upcoming work, we have this space-time perspective where you proliferate fermion world lines along a sheet. So in principle, each ISG of, say, the CSS Floquet code is characterized by a toric-code anion theory. There are fermions that are defined at each instance in time. So you can construct twist effects by proliferating these fermion world lines in space-time. So there's some analogous construction. It doesn't work as naturally in space. You might have to change the short string operators that you measure over time.